All right, the clock says 7 o'clock. Thanks for everyone who's tuned in so far. And I know a lot of you had a rough night last night with the Artemis 1 launch. I know I was up till about 3 a.m. So for those of you who are still awake, congratulations. Thank you. For those who are not awake, however, we are going to be recording this session for later consumption on the YouTube. So watch for that link tomorrow after we get that processed up. And tonight, our president, Tricia Smedley, is on the road still. We'll have her come on after our main speaker, who I'm going to introduce in a second. She'll have some club announcements for us. That'll be the next thing on our agenda. And stay tuned for that for sure. We'll have some announcements about the holiday party next month. So just a spoiler alert, save the date for December 10th. There will be free food. There will be door prizes. There will be cool people. There'll be observing outdoors if the weather cooperates. All good stuff. So more details on that after this program. And following that, we'll have member astrophotos as always, followed by What's Up in the Night Sky with John Pinto. But first, let me introduce our main speaker tonight. Tom Field is with us, so thank you for joining us, Tom. Tom is a contributing editor at Sky and Telescope magazine for the past 7 years, and he's the author of the RSpec software. I'll drop a link for that in the chat. And that received the Sky and Telescope Hot Product Award in 2011. Tom's a popular speaker who has spoken to hundreds of club meetings via the web at many conferences, including NEAF, SAS, AVSO, the NEAF Imaging Conference, PATS, the Winter Star Party, the Advanced Imaging Conference, SCAE, and most importantly now, the Central Florida Astronomical Society. So thank you, Tom. And a little bit quick housekeeping here. If you do have questions for Tom, use the Q&A button at the bottom of the screen there, and we'll get through those at the end as best we can. And with that, I will hand it off to you, Tom. Thank you.
Ooh, quick introduction. Thanks so much, Frank. Yep. And I want to thank you and also Tricia. I think sometimes club members don't realize how much goes on behind the scenes to make these kinds of talks happen. There's emails that go back and forth and coordinating, and the most troublesome is the time zone conversions. And anyway, thanks for helping to make this all happen. I'm really happy to be here. I'm going to speak for about 45 minutes, and then we'll have as many questions as you want. Thanks. There we go. And you know, my background is I've been an amateur astronomer for about 30 years. If you've taken maybe a dozen visual images, you're ahead of me. Was not much of a visual imager, but I wanted to do some science, and it's science that you can do. Not only can you do it, but you can afford it. Your equipment will almost definitely handle it. And it doesn't take a PhD in astrophysics to understand. So I'm just going to walk through some slides here. Let me get things started. First, we'll share my screen, and then we'll go like that. And just a couple more things that I want to do here for myself. And there we go. So Frank, if at any time I seem to be thinking my screen is showing and it's not, because I'm going to go in and out of the PowerPoint show, I hope you'll let me know. So, you know, this is just an absolutely gorgeous photo that came from JWST. And these shock waves just, of course, have just enormous power to basically create stars. And just how lucky we are in our just brief lifetimes at this period of time in human history to be able to see this kind of data and admire it and understand it. But what about all those other stars that are all around these areas? Where are they in their lifetimes? And, you know, how can we understand them? We're not going to spend much time on this slide that I'm about to show, but I wanted to bring it up. First of all, I need to tell PowerPoint to make my mouse cursor always visible. Now, I have to do this every time I come into PowerPoint. I'm in Seattle. Bill Gates lives in the neighborhood, not my immediate neighborhood, as you can imagine. It's on the other side of the tracks. In fact, I think he has tracks that go around his house, so that everybody lives on the other side of the tracks from him. But I'd like to go over and ask him why I have to do this every time. You see, I lost it there. So let's come back in here. Pointer options. If you pause, it has a problem. So we're not going to spend a lot of time on the screen. You've probably encountered the HR diagram before, but I want us to say something about this diagram. Most of us have some passing familiarity with it. But what I found, and one of my topics tonight is that by actually visiting some of the stars and observing them, observing the science and how we identify them, we begin to know our way around this map. And today, literally, I've never used this example before, but today I was thinking about it. When GPS came out, my wife was using a Garmin, and she would follow the Garmin to various locations. And she told me once that she got in the car and she left the parking lot where she had been guided to go to her next stop. And she had no idea which way to turn on the streets because she didn't have a reference. She was just at that spot. And the reason I mention that is because I think for a lot of us, yeah, we've read about Betelgeuse, supergiants, we know, of course, the sun and Vega and a variety of stars. But by placing them on this chart, we get the layout, the map that my wife was missing when she didn't know how to turn left or right. Okay, enough jawboning. This is how we know about the life cycle of stars. This is a spectrum that's been chopped up and stacked here, but these gaps are like fingerprints. So we're going to talk about them and talk a little bit about how you can actually capture this kind of data with your current equipment. Now, you may not have any equipment, and that's okay. My goal is that even without equipment, after you've listened to my talk tonight, that you'll have a good understanding of how we use these spectra. And that will really serve you as you read the literature, whatever it is you're reading, and somebody talks about a spectrum, you'll go, oh yeah, and you'll understand a little bit more about it. So how is it that we've learned about spectra over the years? Well, it's a common quote. We've seen it for years, that we're standing on the shoulders of giants, and we really are. So I was curious about 15 years ago, how to get up there. How do you climb up this pyramid? And who are these people? What about the other people? And these people, I haven't really talked much about this photo, and this is new to the show, but I'm thinking now, this is sort of us that, we're like just looking on. So I wanted to get up here and see what the view was. And how do we do that? Well, we're all self-selected. The fact that we're even here tonight together. Notice I put this word love here. We do love the stars, don't we? How do we learn more about them? And there's tons of ways that we've done that over the years, and lots of websites and textbooks, but there's no unifying principle typically, and no framework for most of us to hang that knowledge on. And for me, although, I could have talked a little bit about star types and things, I didn't really have a comprehensive view. I didn't have the time or interest in plowing through a textbook. So what I found is that when I understood and actually did some of the spectroscopy, when I captured these rainbows of stars and understood where they fit on that HR diagram map chart, that things began to come together. If I was up here on the chart looking at a red giant, then I knew that, down here, I know Vega's here. And I think we are all very spatial in our memory. And so working with spectra helped me organize. And instead of things going in one ear and out the other when I read them, sometimes a smidgen hung around. So let's take a look here. This is Pegasus. This is Pleiades, two P's in my next examples here. So the Pleiades and the Seven Sisters, just keep your eyes on those four central stars. There's an image of them, and here's their spectrum. Now, how do we get that spectrum? How do we get that rainbow? It's pretty here, and this is a pretty highly processed image on just a simple point-and-shoot camera, not even a DSLR. But the key is being able to split the light. Now, for most of us, we've thought it was very expensive, and it was until just the last 10 or 15 years. So this little 1.25 inch grating here is what allows us to split that light. So the first obstacle to you getting involved in this, if you choose to go down this path, is wondering, oh, geez, this is going to cost me a lot of money. $200 for a grating. That's nothing. You buy eyepieces that cost more than that. So, and how's the grating work? Here's where I'm going to stop screen sharing for a second so you can see me here. And back here is a gas tube, just like a neon gas tube. There's electrodes at either end. It's exciting the gas in there. And I'm just going to take this grating and hold it up here so that you can see the spectrum. So there is the spectrum, if I get my finger in there, repeated multiple times. There's the actual gas tube, and you can see different colors in there, right? So that's the rainbow. Now there's those black spots between those lines. This is called the emission spectrum, where there's just spots or lines rather than a continuous rainbow. So you put this on your telescope, almost any telescope, almost any camera, you're going to see a spectrum like the spectrum that we're seeing here. So I'd like to show that so that you see that we're not talking rocket science or expensive equipment here. So that's the first thing I wanted to show. Let's get my screen sharing back up. There we go. And look at how you would mount a grating like this. So you can mount it on a DSLR. If maybe you've never done much imaging, and maybe you've taken some images of the Milky Way and the moon. And with this little adapter here that we sell, you can just screw the grating onto your lens cap threads. You can put the grating on a DSLR. In fact, Barbara Harris, I don't see her listed in the participants here tonight. She's got one of these. I met her down at the Winter Star Party many years ago.
Yeah, she's here.
Oh, she is here now. Hi, Barbara. Nice to hear that you're here. You can mount it on a DSLR on your T-ring and then put it on a telescope or a video camera either. I'm going to show you examples of that tonight. Doesn't have to be a color camera to do spectroscopy, or on a filter wheel. So the second obstacle to getting involved in this, if I can capture your interest tonight, is it's expensive. That's behind us now. And it's just going to be tricky to set up, and it's not. So let's look at a couple more qualitative examples here. These are the 3 stars of the Orion Nebula. There they are. And there's the spectrum. Again, it's a beautiful image in itself. We're not doing any science yet. And I'd like to talk a little bit more, of course, about the science. So let's go to Pegasus. This will be up tonight. You'd be able to zoom in on this little field of view here like I've just done. And what do we have here? Well, sort of being the devil's advocate here, I'd say we've got a lot of boring stars. I mean, for most of us, when we're visual imaging, sure, there's constellations, asterisms, but for the most part, stars seem to just get in the way of the galaxies and other objects we're imaging. Not all the time, of course, but every one of these stars has a story. That's easy for you to say. Every one of these stars has a story, and it's teasing out that story that is just so exciting to me. So what I want to do is take a look at those 3 stars in this field of view, and there is a DSLR image with a star analyzer of that field of view. Now, just if you notice, there's a lot more detail than the previous qualitative views I showed you. Notice that, for example, there's a gap there in that spectrum and in that one, and down here in, if I could draw, I'd be dangerous. So down here, there are some, bright spots. This is what we need to decode and understand. And it's pretty easy to do because these lines are like fingerprints. And so we're really doing, in many ways, we're doing forensics here. And each element, we're not going to do a lot of hardcore science tonight because, to be honest, I don't know it. You can have a lot of fun without being a quantum physicist or advanced in your understanding. And you'll find out in the Q&A that I'm like a really broad river that's really, really shallow. I want to make sure, Frank, they can see me, right? So if I'm gesturing and things, they can also see me up in the corner. Is it working that way too?
I believe so. That's what I'm seeing.
Good. Okay, great. It's hard to know. I'm a panelist here, which most clubs don't do. I'm glad you did because it makes things a little easier for me in a variety of ways. So notice, again, hydrogen has different fingerprint lines than helium. And that's how we're going to discern what it is we're looking at and where stars belong in our HR diagram. So this star here, notice there's a gap there. There's maybe one there, maybe there. This is a little overexposed, the gap there. So this we can locate using that information, and we won't get into the details, as a red supergiant up here, just like Betelgeuse. So now we've got a stake in the ground in this map, right? Now when we observe a type M star or a cool star like a type M star, very cool. This is a temperature scale down here, right? Cooler stars here, hotter stars here. Now we know that they're up here in this quadrant. And so that's the goal of spectroscopy, is to help us get oriented. Let's look at a second star here, and that's this one. Notice this, although it has a gap or two, the one thing that's interesting in it is that emission line there, that very strong little spot. What's that about? Well, this is a hot star, so it doesn't have all the lines that we saw up here, but it has this bright spot. This is a B star, so it's a type B star, and the E, it's a BE star, stands for the fact that it's an emission star. It has an emission line, that bright spot as opposed to gap. And that's the circumstellar disk. I love saying that word. It makes me feel like an adult. That circumstellar disk around that BE star is glowing. And that glowing is what we're seeing right here. And so a B star is going to be in this area, right? It's considerably hotter than the stars over here, and they're very bright. So it's up in this area. Third star, and then we'll move into some other examples, is this star down here. Notice this one is very different in appearance, isn't it? It has a lot of bright spots in it. This is a Wolf-Rayet star. And I want to just show you an image of a Wolf-Rayet star. It's like 25 times the size of the sun. And the bare core is visible because a lot of the outer shell has dissipated. And so what we're seeing here is some of the byproducts of the star's fusion. We're seeing carbon, oxygen, nitrogen, all glowing. This is a late stage star. They can be very hot. They can be up many tens of thousands of degrees Kelvin. So they're going to be, over in this area and maybe becoming a supernova and then ending up as a white dwarf down here. So now, the first time somebody sent me a Wolf-Rayet spectra, early on in my spectroscopy life, I couldn't remember what a Wolf-Rayet star was. I'd read about them over the years, but what I found is once you've actually captured that spectrum, first of all, we love what we create, don't we? Remember, if you're an imager, remember that first image you captured with your telescope or DSLR. And, for me and most of us, it was an overexposed blurry moon, right? So, but to you and me, it was the most beautiful thing we'd ever seen. We showed it to our friends, our spouses, our wives, spouses, and co-workers. That was the third one I wanted to list. So we love what we create. And in that love, again, it helps cement our knowledge as to what we're looking at. So then when we go out and look at online sites and read about these things, we have a way of categorizing it and remembering it. And that's really been a huge advantage. And for me, has deepened my enjoyment of the skies. So I just want to talk a little bit of history here and a little bit of the science just to get us all more or less to the same level. Sir Isaac Newton is said to have been the first person to split light with a prism. And, there's an example of it there. Of course, there's a second way to split light, and that is to bounce it off a finely lined surface like this one. And you can even pass it through a finely lined surface, which is what this grating is. So that was the inaugural spectroscopy that we were doing, which was basically just, hey, look, there's a rainbow and colors are all combined into white light. Now, Bunsen did something more. Now, for many of us, we encountered Bunsen burners like this one down here when we were in school. And Bunsen would take a sample, he'd burn it and then bend the light through and split the light through a prism, and then he'd study the results. And he was a real pyromaniac. He burnt everything he could find practically. And the great thing is he kept good records. And we use those records, and we'll see those in a few minutes. One interesting thing about Bunsen is he deliberately did not patent the Bunsen burner. He said, this is for the betterment of humanity. I'm not patenting this. Anybody can use it. Now, we wouldn't see that today, would we? It's a different attitude we have today about those kinds of things. So Kirchhoff was a contemporary. We're not going to talk much about him this evening, except on this next slide, two quick examples, not a lot of detail. And that is, there's two different types of spectra you can get. You can get a rainbow with gaps, or you can get more or less a blank field with lines. Now, the interesting thing is, whichever you get, the lines are at the same place, whether they're gaps or lines. Which you get depends on things that Kirchhoff talked about, but we won't tonight. The temperature of the gases involved as the light leaves the star and stuff like that. But so we'll see examples of both of those tonight. Now, we saw this slide before. I just wanted to give one more detail before we move on to more examples. And that is this hydrogen. Of course, hydrogen is very common in our universe. We've actually given names so that we can talk about the absorption or emission lines in hydrogen. And many of you know this. Bear with me. We're almost past this review for you. So this line here we call the hydrogen beta line. And what color is that? That's, let's call that robin egg blue to be very unscientific. So the hydrogen beta line is robin egg blue. Now, one more chart that I created it, and I love showing it to people, unless it scares them away, because there's far more on this than I know. But I wanted to show you that hydrogen, of course, has a very different fingerprint than helium. So there's that robin egg blue line for hydrogen. It just doesn't exist on helium here. Neil deGrasse Tyson, by the way, told me that he has this poster hanging on his office wall. Now, it's not like I sit down and have tea with him all the time. The truth, I guess I should pull the curtain back a little bit. He told me that after I'd been standing for 3 hours in the pouring rain outside a lecture hall here in Seattle one night. I'd met him the year before and given him a poster. And then a couple years later, actually, he told me he loved the poster. And I keep scheming to get him to shout out on his Twitter feed. He has 13 million followers. So it wasn't just altruism that I gave him one. He doesn't really endorse products, but he loves spectroscopy, and we had an interesting discussion about it. Instead of being the celebrity that people were crowding around to sign things, when I came up and started talking spectroscopy, he flipped into being a scientist and wanted to talk about what people were doing. It was fun to see that. And I feel bad for the celebrity chasers because we just went down the rabbit hole of science. So what do almost all the astronomers, except for Neil deGrasse Tyson, have in common so far in what I've shown? They're old white men. The field has lots of people who don't fit in that category in it, and I wanted to show a few here because I think it's important to recognize them. Many of you have read about Annie Jump Cannon here. She and her team of women called computers were prohibited a little more than 100 years ago from accessing the telescopes at Harvard. So what they did was they studied the photographic plates, and they literally analyzed hundreds of thousands of them. And with their attention to detail and insight, they came up with a stellar classification scheme that helped us understand the stars. It's a remarkable and huge accomplishment. Priyamvada Nataraja is at Yale, and she studies black holes. Nancy Grace Roman down there in the lower left-hand corner, she was the very first astronomer at NASA in the late 1940s. Imagine the challenge of that role. And down here, Elisa Quintana studies exoplanets around cooler type M stars, looking for signs of ET, basically. And finally, Dr. Eisler here is at Dartmouth, and she studies black holes also. So this was a fun slide to put together. I'll postpone talking about Neil deGrasse Tyson until later in my show in the future. But again, there's a lot of recognition that's due to some of the giants who came before us about whom we haven't heard much. Okay, thank goodness we're done the history, theory, and equipment and can get on to the pragmatic stuff. All of that was important, but we want to understand and do things. So what happens when you put a star analyzer in the light path in your equipment? Well, it splits it. Some of the starlight goes straight through and some of it splits into a spectrum. And that's what we studied. So I want to show you, this slide has a lot on it we won't be discussing, but I wanted to show you just briefly 2 examples. So this is, and that's not what I wanted to do. So let me come back here and pop that slide up again. There we go. And that's not anywhere near where I wanted to be. Rookie mistake on my part, but we'll get there. Hang in there with me. So there we go. That was the slow way to get there. Thanks for your patience with me. So the deal is, that's hitting the escape key rather than F1, by the way. These are the hot stars at the top, And then we go down here to the cooler stars, the type M stars. So these are all separate spectra captured by Torsten Hansen with just an 8-inch Newtonian and a video camera. So another obstacle people have to getting involved in this, they go, oh, I'm going to need to do these long exposures, go to a dark sky site. This is a video camera. Now, these are bright stars. Normally, bright stars don't have much of interest, but there are thousands of bright stars that we can image in, literally half-second, 1-second exposures. And the other thing I really wanted to shout out about, and that is that, we all suffer from light pollution now, right? But spectroscopy is really much, much less effective. And I say much twice there because it's much, much less affected by light pollution, because with visual imaging, we're really concerned about fine gradients. With this, we're looking for gaps in the spectrum, right? We're looking for absorption features like this. So 2 quick examples. Notice these cool type M stars down here have these wide bands. It's not just lines, it's like a huge forest of lines. Well, these cool stars, these type M stars down here, are cool enough that a more complex molecule can survive on its surface without getting burned up. And that's titanium oxide. To be honest, I don't know anything else more about titanium oxide. If you care to, then you can read about it. That's the great thing about being the adults we are. There's no quizzes. We get to choose what we read about. The other example I wanted to show you on this page was this area right there. Notice that these hotter stars have this really fairly significant gap that doesn't show up on the cooler stars. And in fact, this gap right here on this type A star like Vega is most pronounced. Just a quick review as to what's going on and causing these fingerprints. The Bohr model of the atom has electrons jumping around, and when they jump from shell to shell, they can absorb energy. So this absorption here happens when in a hydrogen atom, an electron jumps from shell 2 to shell 4. That's all the science we need here. There's plenty more to be learned if we care to, but that's all we need. So that absorption occurs on these stars, but these stars aren't hot enough to cause many of the electrons to do that kind of jumping. So this is how we use these fingerprints. But let's take another step. Suppose that Hubble, the Hubble Space Telescope people, they made a big mistake and they gave me time on the Hubble Space Telescope, and I used the spectrometer and I observed a little absorption feature there, and I wrote a paper and said, oh yeah, I meant to show you that while we were here. This absorption feature is in the robin egg blue, right? That's how we know it's this hydrogen bomber transition. So if on the Hubble Space Telescope, I observed a tiny absorption feature there, barely discernible on your screen now, and I tried publishing a paper and referred to it as an absorption feature in the robin egg blue region, I'm not going to get published, am I? So in order to do science, we need to quantify this. And that's what we do by graphing the intensity of this region. So the star here, this is intensity, this axis, and the star has a huge peak because it's very bright, the light that goes straight through the grating and didn't get deflected. Now over here, we've got, this data is really weak out here in the wings, so that we have very low levels here. And notice that barely discernible dip is really clear here. So this is how we do science, is we convert this qualitative data into quantitative. Now, how do we do that? Now, listen, I know it's evening there. A lot of you were up late, and I'm not as dumb as I look. I'm not going to do a full-blown software presentation, but I do want to show you that there is no obstacle to your learning software that does this. So my story is, I went out with a star analyzer-like grating 15 years ago or so in my backyard, right out that window, 3 miles from Pike Place Market here in Seattle. And this is literally the spectrum I captured. I came in that night. It was Vega. My blue jean knees had grass stains on them because it was Vega. And, I don't have a lot of sophisticated target acquisition and tracking software, even though it was a C8. So the next morning, I tried to create one of these graphs, and I used some of the shareware that was out there, and I couldn't. I really struggled. The software was crashing, and to add insult to injury, the error messages were in French. So I gave up. I literally did. I took the star analyzer, I put it in its case, and I put it in the drawer that's right down there, right on the floor. There it is. It's still open, actually. It's probably been closed a few times since. And I gave up because I told my wife, it's supposed to be fun. This is a hobby. I'm just struggling. But it kept bugging me over the next couple of weeks. So a few weeks later, I decided one weekend that I just write something to create this graph. And I had something that created the graph, after a day or two, I was good to go. And now 10 or 15,000 programming hours later, the software is almost done. My wife keeps saying, would you finish the software so we could have dinner at a decent hour consistently? So it became a product, but that wasn't my goal. I wanted to do this myself. And I want to show you just 120 seconds, I hope I can keep it to that, of the software. So this is a typical image view that you would get from a FITS image, from a live video camera, like a ZWO camera. It doesn't have to be color, but color clearly is more intuitive here, isn't it? So you can see there's a gap there. There's maybe a gap over here in the robin egg blue, right? So all you do is bracket that region in with these lines, and then over here you have that intensity graph. So this peak here is from the star's intensity. And of course, this area over here is from the spectrum. And that dip right there is that dip right, not quite pointing to it, right there. So we've now, what did we do? Listen, PixInsight is an amazing program, but it doesn't have a learning curve. It has a learning cliff, right? And you either fall off it or you have to learn to scale it. And the view's great at the top, but the learning curve in the software I'm showing you is virtually zero, really. I mean, literally, you're on the, either video or image tab, you open your image and it comes in, you move the lines around, you've got your data, but so what, right? The second step is, what about all these dips? What kind of science can I do? So another spam call on my phone. So I wanted to show you what we can do if I can figure out, this is the second time I've had this problem. I don't know how to move there it is. I wanted to move the little zoom window out of the way. I'm going to pop up this little reference, which is based on that data that I mentioned that Bunsen collected when he burnt things. So, and let's come down here and say to the software, when I put a check mark here, I'm saying, would you overlay the graph showing me where the hydrogen bomber lines should be? And look at our data. Wherever there's a dip in our intensity, like some of these dips over here, we see a dip where we expected it to be for the hydrogen bomber lines. Now we're doing science. So, and I mean, we can make it prettier. We can, fill it, and it's a great teaching tool. So that's all I wanted to show you here. Now, this is actually a frame. I stopped the video playback. This is from that first night out. You can see it's jumping around here because my seeing is changing, right? And there's some very simple stacking capabilities in the software. You can see it's stabilized after, at 4 frames per second, after 10 or 15 frames, a few seconds. So this is not hard to do, I assure you. And it comes with a huge collection of really short tutorial videos made by me, with screen captures, basically. And I walk you through all the different steps. So it's really easy to learn. So we're going to leave this screen and maybe not come back to it. I want you just to remember this screen here. This is Vega with our absorption lines, our hydrogen alpha, our hydrogen beta in the robin egg blue region, because we're going to see that more in a few minutes in another slide. So here we are back here, and that's how we create these curves. So let's come back. This is that Pleiades view that we saw before. We saw it as a qualitative view before, right? It's pretty, I was talking about fingerprints. But this is where you can call my bluff and say, well, okay, that's pretty, but how do we actually analyze that data? And that's where you use my software. Just to give you, we're not going to go through all these examples, but here's the Pleiades. And here you can see that each one has its own curve, and they look different. They're not all the same. That's how you can do science. It's just throwing your image into the software, bracketing in a star, and observing its properties here. Now, to be honest, most of the time, we're not on the path of discovery. We're duplicating some of the steps that the giants took. For me, what I found is, and I've never said this in the talk, I'll see if I can say it so it sounds appealing, is I find that I can now read journal articles that are, say, 40 or 50 years old and understand a little bit and actually have done some of the things they're saying. Now, sure, I'd like to come closer and closer to the present, but even being able to do that kind of correspondence between the steps of the giants and what we've done in our hands is really exciting. So that's my software screen. You saw it a moment ago, and I also showed you the gas tube running. I'm not going to do anything else on this screen except to point out that if you're an educator, we have a little tiny handheld gas tube spectrometer for the classroom. And for everybody, if you're looking for ways to get into the classroom, what I'm talking about here, listen, astronomy is not a big topic in our schools. It's part of the new science standards in almost every grade. But educators have so much to cover, they don't spend much time in astronomy. But you know who does? Chemistry teachers and physics teachers. Chemistry teachers can't avoid it. It's the heart of how everything works. So they use gas tubes, but typically they, like this one or the one you saw over my shoulder, but they use these handheld devices that just, the technical word is they really suck and they're really frustrating. So over the years, literally thousands of educators have started using these kinds of cameras in our camera in their classroom. Educators from Ivy League schools, a handful of Ivy League schools, Dartmouth, Yale, all the way to home educators, high schools. And you can use that as a tool to get into the classroom. It's hard to say, gee, I got a telescope. Can you get all your students to come in tonight or one night and we can look at some stars? But it's pretty easy for you. And again, I'm selling you on spectroscopy. I don't even care if you don't use our tools. Use anything you can find. But if you've got a presentation that uses gas tubes, and you can even transition into astronomy and talk about how these stupid gas tubes are the same thing that we observe on stars. So if you're looking for a way to get into the classroom, I can pretty much guarantee you that if you can polish up a short presentation, and I'm happy to work with you on that, you can go to an educator in your school. And even under the auspices of the club, you get a little bit of validation or authenticity, legitimacy. You know, when I first started doing the spectroscopy stuff in 2010 and telling people about it, I had a crisis in confidence. And that was what I was showing people was unbelievable to them. And me too, before I did it, that it would be so easy and so exciting and so cheap and all of those things. And I really felt like people, you know, like I was just or being seen as some whack job, you know, some weirdo, some eccentric, you know, like some of those old men that we see at NE for a winter star party, of which I'm now one, at least in age and gender. But you get some legitimacy and you can actually serve in the classroom by doing this kind of thing. I've never spelled that out or spoken about it quite at the same length I just have. But again, I just think it could be a tremendous gift for you to the education system, in addition to the standard outreach that I know some of you do. So you can do what I'm showing you here at star parties. Of course, you probably wouldn't want to do this at a dark sky site. This is in Marseille, France. So let's look at some objects here, our beloved Ring Nebula. When we look at the spectrum of it, it's not quite a rainbow, is it? Well, the object is repeated all the way across, but in this case, thank goodness, there's really only two elements glowing in M57, hydrogen and oxygen. That O stands for oxygen. Most extended objects aren't going to be this interesting because they have much more lines. So for extended objects like M31 or close-up, you know, objects, typically we need a more expensive device. I just, for completeness, wanted to show you these. You can see they're considerably more expensive. You're tracking on a 20 micron slit. It's a big jump to start with these. I only know of one out of many, many people who, or maybe a handful, two or three, who have actually started this way. It's just too big a step. And it's too big a commitment financially if you're not sure you want to do it. Now, here's M42, our beloved M42. And again, you can see this is with a slit spectrometer. I want to make it really clear that almost every example I'm showing you tonight, and I'll call out those that aren't, are done with a grating. And that's because I think sometimes we get misled when we look at gorgeous images and think, gee, I want to do that. And then we look at the fine print, like in the back of Sky and Telescope or Astronomy Magazine. Maybe you were like me when you just were getting started. You looked at those gorgeous images of M31 or M101, and you went, I want to see that. You know, I want to photograph that. Then you find out it's not so easy, right? But everything I'm showing you is not that. It's something done in a really simple setting. So I'm going to stop screen sharing for just a second here. And I don't know whether it's possible in a presentation like this, but I thought I'd ask if people can, if anybody wants to unmute themselves, I'd love to hear the first time that you saw M42. What was your experience? Where were you? How did it look? Any takers? Anybody want to jump in and do that? And I certainly understand if you don't, that's fine too. But it was, you know, it's one of the things that we get introduced to typically fairly early on. Okay, since we don't have any oh, there we go.
We have a hand raised. I'm trying to figure out how to do this. We're in a webinar format, so people can't talk, unfortunately.
Oh, that's okay. Well, go ahead.
Well, we got a couple here. So let's start with William Pittendray.
Hi, William.
Okay, can you hear me?
We can. Hi.
Okay. Well, I happen to be the one who discovered Orion's Nebula.
Now you're talking, William.
You know, I was just, I had this little Jason telescope, probably a 90 millimeter, and I was just out there just moving it around from place to place, had no clue how to find anything. And I came upon this nebula. I'd used that telescope for the moon and Jupiter and Saturn, which I couldn't see much of it. But I had no clue what I was looking at. I ran inside, told my dad. He came outside. He had no, the internet would have come in real handy back in 1963. And
that's great.
So
what did it look like?
Amazed by it. But I do remember the result of this. He did find out what it was. Mm-hmm. And in a short time, I went up to my second telescope, an Edmunds catalog 4-inch reflector. You remember those?
Mm-hmm.
So this was really my mark in serious astronomy. So it was exciting.
Congratulations on your discovery too. I'm just,
Sadly, I later found out other people had discovered it before I did.
Oh, that's okay. And actually, it's a perfect answer, because when we discover something, whether we stumble across it or we walk down a path that somebody else has already tread, there is that excitement. And yeah. I would think that if your experience was like mine, then you went and read a little bit. Eventually, when you found out what it was somehow, if I may ask, how did you finally identify it? When did that happen?
Well, my father did that. I was in the third grade.
Wow.
And my father had a friend who was an astronomer, an amateur astronomer. Mm-hmm. And he asked about it. I do remember that we made notes, observing reports, basically. I drew a chart of where it was in the constellation Orion. I drew a simple image and made some notes about it so we could find it again. But of course, it's not difficult to find.
Yeah, well, thank you for sharing that. Congratulations. It's a great story. And I really appreciate your stepping up. In fact, you need to come to all my presentations and tell that story, because it's a good one.
Okay, Tom.
Thanks, William. So
I do these stories free of charge, but there's a $100 handling charge.
Okay, well, we'll talk afterwards.
Okay,
we'll work something out. So my experience was, and you can mute your mic when you're ready. My experience was in the early 90s, Shoemaker-Levy was coming. I wanted to do some of this astronomy stuff. I went to a first quarter star party in Denver, actually. And, you know, it's interesting, as you heard with William, to remember back when you didn't know something. And for me, I had no idea what I was going to see. I got out of the car. I walked up on the berm over the observing field. And when I looked out on that observing field, what I saw, to my uneducated eye, you know those cannons at the circus that they shoot people out of? That's what I thought I was seeing. You know, they were Dobbs. I had no idea what a Dobb was. So I walked down onto the observing field. There were people much like many of you running the telescopes, explaining that we were looking at the birthplace of stars and we should be really excited. And when I got up to the eyepiece and looked through it, to be honest, I was really let down. It was a smudge. I was expecting something like you see on your screen. So, but even with that experience, or Williams, I've gone back and looked at it repeatedly over the years. Now, of course, better telescopes, better locations for observing. And the other thing is, we've gotten, you know, we understand how to use averted vision now, right? To look at things indirectly that are dim. But I'll tell you, and the reason I spent probably more time than I should have on M42 just now is when we come to the eyepiece with an understanding of what we're looking at, the visual experience is that much richer. And so as we build up our knowledge, our foundation, and when we come back to M42, we know it's a stellar nursery and various details about it, it gets more interesting, even if it's still just a mono smudge. So anyway, that's my M42 story. I want to show you a couple other additional examples. Over here is, if we'll go the right direction, is Uranus and Neptune. And you can see the spectrum here. And this is also done by Torsten Hansen with a video camera. This was an imaging source camera. You can see the deep dip and the forest of lines down there. So forest of lines that we saw on type M stars earlier means something's pretty cool, so complex molecules can survive. We're seeing the atmosphere, the methane atmosphere on these planets. Now, 60 years ago, professional scientists would have given their left leg to see this kind of thing, right? And now we can do it in the backyard. And of course, this is how we'll finally, if we do, discover signs and evidence of extraterrestrial life by analyzing the spectra of some of these exoplanets. So in 1881, Henry Draper observed the spectrum of a comet. Heck, if Hank can do it, so can we. Here's a comet. Down in the lower left, you can see this little string of jewels. It's an extended object, but it's compact enough in the core that we don't need a slit device. So over on the right, we can see the peaks. These are called the swan bands. And this was captured by a guy in India named Vikrant Agnihotri. When he came to me in 2013 or so, he was a beginner. He knew nothing. He's now like way beyond my level. But I'll tell you, when he came to me in 2013, he's in India. I thought, okay, you know, I'll give him a big discount. You know, he's from a country that doesn't have a lot of money. Again, that was my cultural centricism speaking. So I gave him a discount. He sent me a photograph a few years later of his setup, and he's got like a C-14, and he's got all this equipment. No more discounts for him. So here's another more timely example, comet Neo-Y. You can see the sodium doublet, also done with the star analyzer. Now listen, anybody who uses, and we can see it over here if I get the right key, a C-clamp as part of their setup is my kind of guy. So Robin Leadbeater, who's the designer of the star analyzer, basically put a grating on a video camera and observed a meteor. So this is the meteor track. This is the spectrum. It brightens here. This is, again, just an outburst of bolide. And here we can see the spectrum. Listen, if spectroscopy is a niche field, this is a niche and a niche, right? You got to wait a while, and there's some challenges to doing it. But some people do it, and it's pretty exciting for them. We're not going to spend much time talking about the sun tonight. We've heard a lot about it. We'll be hearing a lot more in the next couple of years. During total eclipse, the flash spectrum can be looked at with a simple DSLR. So let's just leave that there for now. Just a quick review about what Doppler shift is. A couple days ago, I did something not stupid or unsafe, but sort of irritated a car that was coming towards me. I mean, what I did, now I'm never going to tell this story again, bad introduction. I didn't pause to let somebody turn in front of me at a stop sign. You know, you're supposed to yield and all those things. And I'm embarrassed, really embarrassed to tell the story. But the point is, he honked his horn as I went by. And what did their horn sound like? It sounded like, right? High as it's coming towards you, low as it's going away. That's because the sound is as if stretched as he's coming towards, and is coming away and compressed as he's coming towards me. High, low. Same thing happens with light. So if we're expecting a triplet here, I love that term, self-defining almost, and instead of seeing it there, we see it moved over to the right, we know that object is moving away. That light is red shifted. On the other hand, if it's moved to the left, we call it blue shifted because it's moved towards the blue, and that object is coming towards us. Let's see how we can use that to do some pretty amazing science. So here's a type 1a supernova. Again, briefest description ever of a type 1a supernova. Two stars orbiting each other. One's bigger, mostly, usually, than the other. Somehow some gas gets sucked in by this one, and it explodes. So in M101, there was a supernova. There's a photograph of a supernova that was closer to us many centuries ago. You can see, looks like a shell expanding about it, right? So there's a spectrum that David Strange captured with 15 minutes of integration time with a C9. And there's the spectrum. And there is a very deep absorption dip, right? Professionals use this as a fingerprint to identify this type 1a supernova that happens with two stars instead of just a solo star running out of fuel. Now, this next slide is not going to be on the quiz, but a type 1a supernova has this very deep dip right around 6,000 that helps us identify it. None of these other supernova types have that dip right there. So one thing we can do with that dip, we can notice what wavelength it's at. And really quickly here, with one addition, one subtraction, one division, that's it, no higher math. How fast is that shell of the supernova that in M101 coming towards us? Well, we take that wavelength and make a note of it. We look up on Wikipedia, if Bunsen had burnt beach sand, it would have been at that wavelength, silicon. These two are different, and that's from Doppler shift. There's the Doppler shift formula from Wikipedia. I wouldn't remember it. And there is our division, subtraction, and multiplication. And now we have calculated the blue shift from the shell of that supernova coming towards us. There should be two wows there. One is, wow, that's a big number. And the second is, wow, I can't believe I did that with such easy, inexpensive equipment. So, and this is how, as I said, professionals identify supernovae. Adam Rees won the Nobel Prize. He and his team, just before the turn of the century, observed the accelerating cosmological expansion, and they used, like many professionals, type 1a supernovae as standard candles. Now, their footsteps are way out ahead of us. You know, their shoulders are way above where we can climb. But it is fun to be able to observe a supernova and identify it. And we can now do that. I'm going to, if I have time, I'll comment on him actually noting my improper usage of technical and scientific language in my first publication in Sky and Telescope a little later. What about the spectrum of a black hole? Now, of course, a black hole itself doesn't emit light, but the matter in the accretion disk that's spiraling in gets very hot and glows. And so we can take a star field, and thank goodness David Hayworth knew where to find 3C273. And there's its spectrum. And you can see two little dots of light at the peak, at the points of those arrows. There they are. And there's the light curve. Now, when I'm giving in-person talks, I always, at this point, look around the audience to see if there's anybody in their 20s. Because this guy was in his mid-20s when he looked at this spectrum. And there's a beautiful transcript of an interview with him on our site. I can get it to you if you just want to contact me via the site, where he describes this discovery and the challenges, the fears, the impersonator concerns he had. And it's fascinating. As a scientist, what's something one often does, takes an unknown and compares it to a known. And that's what he did. He looked at the bomber lines, and this is a screen capture from my software. I asked you to sort of keep it in your mind's eye so you could remember those bomber lines. And he said, well, do they line up? Is there a dip or a peak there or there? Is anything? There's nothing going on here that would match those lines. So he concluded, well, whatever's on this object, it's not hydrogen, except it was. And he figured it out. And he was afraid it was too easy once he stumbled across it. But again, there's a lot of prep to that stumbling. So what he had discovered was this object was so far away, given the Hubble constant and calculating its distance, that it was astonishing that at that distance, we could still see it. It must be unbelievably bright. And in fact, I love this. In fact, on your site on Facebook, you've got a What's Up Tonight, and it talks about Pollux and on the eastern horizon in the early part of this month. You know, Pollux is pretty close, but I love this. If this quasar was where Pollux was, it would be as bright as our sun. So what amazes me is this light that has come such a great distance over such a long period of time still has information in it that allows us to know something about this object. It's like it didn't age, right? Unfortunately, humans age a little differently. Here is Martin Schmidt a few years ago. You can see he changed a little. He's since passed away. People accuse me of throwing him under the bus with his hair there. And, you know, I'm just jealous of the guy. What can I say? So this is a beautiful image. And in my first Sky and Telescope article, I called this Doppler shift. And at that time, Bob Noye, editor-in-chief of Sky and Telescope, forwarded my article to the guy I showed you a minute ago who won the Nobel Prize, this guy, Adam Rees. And Adam Rees, who had not yet won the Nobel Prize, he was going to win it later that year, said, and Noye knew this, he was just seeking collaboration and corroboration, said, no, that's not Doppler shift because nothing's moving. Again, we have cosmological expansion. That really stretched my mind to think about the precision in language and what that meant. So this is the kind of fun learning that we can do. I've got two more quick examples and we'll finish up. So far, we've been looking at objects, basically the hydrogen bomber series, mostly. And how wide are these features? If we drop, some lines down to the x-axis, right, they're about 50 angstroms wide. What if we want to drill into the details here? Then again, we need to use a higher end device, one of these slit spectrometers. Then we can compare a known star or an unknown star to the moon, and the moon isn't really moving towards or away from us, and see the Doppler shift, the radial velocity of that object. So this, as I said, requires a slit spectrometer. So final example of the night, and that is here. So, and I have a prop I'm going to hold up. This is a rotating star. In this case, I'm going to show you one that's rotating very fast in a moment. This edge is coming towards you, so that light is blue shifted. This edge is moving away from you, so that light is red shifted. So the light is being both red and blue shifted. So this is what's happening. The approaching edge is blue shifted. The receding edge is red shifted. And if we look at Altair that is spinning very quickly compared to Vega, notice that this feature is compressed and spread out a little bit. That Doppler shift is what allows us to measure that. Now, I've had three examples just now of Doppler shift. There's other ways that we use spectra to study the stars. I think these are some of the more engaging ones. Now, this might be a moment, just, my wife talks about dressing for success. I don't think, in fact, she assures me this is not what she meant. But there's our hydrogen alpha line going right through there. So let's talk just for a minute to finish up how you might want to get involved in this kind of thing yourself. What do you need? Well, you need a star analyzer grating. You need almost any camera, as I showed you way early on. You need some software. There's my software. These are the French software that I mentioned, both of them. I know the authors, and the software has improved a lot. It still has some of the drawbacks that freeware sometimes has. But the authors, as well as the software, really helped pioneer. Just wonderful people wrote this software. And the other thing you may need is a spacer to set this distance between our grating and the sensor on your camera. It's not critical like focus. And there's tools on our site as well as me to help you determine whether you need that. So it's pretty easy to get started. The other thing is, when most of us, older as we are, learned all this, we didn't, we had to, especially if we were in third grade, we had to go to other people and other sources, right? Of course, with the web now, there's so much material. And now, because there's more and more amateurs doing this kind of thing, there's tons of books out there which are fantastic reference works, this being one of them that I have there on the screen. I don't have time to talk much about it, except I want to show you that, again, it's got a fair amount of prose, but it's aimed at amateur astronomers. So this is not, there's no math involved. It's a great learning tool to look up the things that you've imaged and understand a little bit more about what you're seeing. And to be honest, there's lots in here that I haven't read and don't understand. On our site, I call out, again, on the link, I call out this book as well as some others. You'll see there's some Patrick Moore books on all of this now, which get a little bit more into the theory. But all these books are good books, which is why I have them listed here. And I make about 10 cents when you buy a book. I think I've made about $40 over the years. But interesting thing you may not know with Amazon, if somebody buys a product having gone to the site through one of my links, I get cash back if they buy anything. And although I don't know who they are, it enumerates what they bought. So I've made money when people have bought My Little Pony dolls after going out to look at spectroscopy books. This is a funny title, Astrophysics is Easy. I always was a little uncomfortable riding the bus with that under my arm. So, but this is the kind of thing that a book like this can help us with, to not only explain what we're seeing, but also why. So the other thing, of course, is the online forums are fantastic for learning now. There's tons of people out there who want to help all of us learn. On our site, you can download the software for free for 30 days. I taught a workshop to the AVSO some years ago to 100 people, hands-on, in person. It's recorded, it's on YouTube, it's linked to from our site, and the sample data is there. So you could tomorrow morning download the software, the sample data, and then preferably on a second screen, you could watch the workshop and you could follow along on your screen, even if you don't have a telescope and never plan to do this with your own data. There are more and more opportunities coming, as well as some today, for pro-am collaboration. Most of these are amateurs. Bob Stencil is the professional at University of Denver. I think he was there that first night I went out and saw those circus cannons. So we have now strolled through the HR diagram. We saw an example here. We saw in my software, we saw Vega, my first capture. We saw a B star, right? And we talked about Wolf-Rayet. We saw some other stars along the way. As we get those stakes in the ground, the science becomes easier to remember and understand. We've come a long way in the last 45, 50 some minutes. And thanks for your patience. I went a little bit over. I apologize. We've also, of course, come a long, long way in the last several hundred years. This edifice of knowledge that humanity has built that has given us things like vaccines for viruses is just astonishing. And we get to participate as amateurs, which is so exciting. Thanks for your attention. Thanks for the outreach that you do. I'm always available for questions, even after the meeting tonight. I'll stop screen sharing and we can talk if you've got anything to ask.
Yeah, we do have a few questions that have come in, Tom. So first of all, thank you for that talk. That did not feel like an hour. That was a lot of fun. So I learned a lot.
Great.
Appreciate that. One question for myself first before I get into the other people, because I can do that. So you mentioned AVSO, right? So is there like an organization that allows amateurs to pool their spectroscopy observations together and make that accessible to the world?
Yeah, you can start coming to my talks too. William, he's going to cut into your finder's fee here. Yes, the AVSO has a database now, and there is a person who is assigned to vet the spectra that get submitted. They are ramping up their efforts and have been for some number of years. The person who is the moderator for that data and screens it is a woman who's in her early 20s, who we met at a spectroscopy conference, and she was just a rank beginner. She now works for Sarah Seeger at MIT, who is a world-known researcher. I had to look her up. I didn't recognize the name when I first heard it. And she got to that position with the help of people like me and others, as well as the AVSO. The former director, Stella Kafka, helped her into that position. You all can help people grow in the field too. There's also a database in Europe called the BE database, as well as one in Spain. So we can contribute data. To be honest, it's not as active as I think we're going to see it in the next several years, because there's more and more people. We're getting to the point where there's a critical mass, and the scientific community is beginning to really understand this stuff. And that by stuff, I mean that we can help them. We don't have big instruments, but like with photometry, we've got a lot of instrument time if we want it. So good question. Thanks for asking that.
Very cool. Got a couple more here. But first, William Pittendray Observes just wants to point out that the Astronomical League has a spectroscopy observing award as well. So if you are going down this rabbit hole, you can get recognized for it as well.
Yes.
Barbara Harris also just wrote in. And by the way, thank you, Barbara, for recommending Tom as a speaker. I appreciate that. And thank you, Tom, for taking this on short notice.
Thank you.
Barbara says, also not a question, but a comment. This is extremely to do, and Tom is very helpful to determine how to set up your equipment. The second star that I did a spectra of was featured on Tom's website, P Cygni. So it's very easy to do and very satisfying. So good little testimonial there.
Who was that? Oh, from
Barbara Harris.
Yes,
yeah.
Yes.
Cool.
Great.
And now for some questions. Oh, go ahead.
No, I was just going to say, one of the great pleasures I have, this is not a career, it's not even a big money-making business. My pleasure is introducing people like all of you and having a chance to meet many of you. And I met Barbara, as I mentioned, at the Winter Star Party. Any of you going north to the NEAF conference in April, I guess this will be the first time since COVID, we'll have a booth there. And if for some reason you're out in Seattle in January, the AAS professional conference is here, and we'll have a booth for that too. But go ahead. What other questions do we have?
Cool. Yeah, and if anyone else has a question, just hit the Q&A button at the bottom there, and we'll get to it. We have one from John Pinto. John Pinto asks, is there a way of using these spectroscopic images to identify the different population stars, 1, 2, or 3? Basically, which generation of stars does a particular one belong to?
Yeah, in order to do that, you need to look at abundances. In other words, how wide are these absorption dips or peaks? And for that, you really need a slit device where the width isn't being affected by the size of the star on your sensor. So that's a more advanced topic, but that's exactly how professionals do it, is by looking at those ratios of different elements. So it is doable. Now, those stars may be very distant that you're looking for. Truth in advertising here, when you put a grating in the light path, the same number of photons that normally fall on a handful of pixels when you're visual imaging are now spread out across hundreds of pixels. So you lose, I mean, I hate saying this, you lose 5 or 6 magnitudes. Now that's like an, oh my God, shoot me now kind of statement for most imagers. You know, we're all digging for low magnitude stars that we can image anyway. But the good news is all those 5, 10, 15,000 bright local stars that we normally don't have any interest in now become interesting because their spectra have something to show us. So that magnitude loss isn't that important. But when you're trying to image really distant objects, as if I'm pointing them out here, you do have that loss of magnitude to deal with. You can stack images, all those things can be done. One other quick aside, and that is one of the reasons I didn't like visual imaging is that I really couldn't discern the subtle aesthetic differences. There used to be a large format book entitled Astronomical Image Processing with Photoshop. And you'd open up 2 facing pages, and on one page they'd have a before and an after of some procedure they'd done. And I'd look and go, well, I guess I see the difference. So for my eye, it didn't really make that much difference. And the good news is with spectra, we don't want to do all that post-processing. I mean, eventually, if we're really doing higher end science, we might do darks and flats and those kinds of things, but we certainly don't do any of the convolutions or any of that processing because we want the photons to be processed by our software exactly as I hit our sensor, not skewed in any way. So that really unburdens us from having to learn all those complicated procedures. We're looking for data, not pretty. Anyway, go ahead. What else?
Absolutely. All right, we have one more from Mark Pernell. He asks, all of your spectra images show the star to the left and the spectra to the right. When I try, I get spectra on both left and right side of the star. Is my result normal?
That is normal. And I'm not going to dig for an example of it here well, maybe I should on my computer. But what Mark says is the case. When you split light in a grating, you see the star in the middle, and then there's a spectrum on either side. That's the physics of it. But with the right instrument, it's designed to put more of the light in one of those orders. These are both called first order. The star is called zero order, first order. And so whichever the brighter of the two, Mark, should go to the right. And that's basically how you deal with the fact that they're two. Now, the reason you didn't see those on the examples I showed is I shoved the stars all the way over to the side so that the weaker, uninteresting spectrum was off screen and the brighter one was on screen. It's a great question, though. Thanks for asking it.
Cool. Thank you. And that is the end of the questions that we have. So with that, I will let you wrap things up. You have any parting thoughts or anything you want to leave us with?
I don't. I want to, again, I mentioned it earlier, for those of you who are doing outreach, it's certainly an important activity for us all to do. And I'll just, at the risk of going on too long, I just want to tell one quick story. I was down at Pike Place Market about 5 years ago. I had my Lunt telescope set up there as a Lunt 100. I'm showing people passing by. As it turns out, it's not a great place to do outreach because people are either excited to get into the market or they're just exhausted, get me back to the car. But while I was there, and there's some street people who hang out there, just hanging. One of those people hanging came up and said, "Hey, can I look?" Yeah, sure, sit down, take a look. He spent a long time looking. And I'm doing my little spiel that some of you do, distance to the sun, and those arches are like the McDonald's arch that you could drive the earth through, standard stuff. And he pulled away from the eyepiece and he looked up to me and he said, "How did you learn all this? How did you learn all this?" And at that moment, I appreciated just the great fortune that we all have had, that we've been able to figure out how to learn all this. And so when you do outreach, you're giving back. And so thank you all for doing it. Anyway, with those parting words, I'll shut the F up. I'll let you all continue with your meeting business. Thank you so much. And I'm always available for questions. Thanks again.
Thank you, Tom. And you're certainly welcome to hang out if you want to. But if you want to get back to life in Seattle, where I'm also from, by the way, great place.
Oh, really?
Yes.
Cool. Great.
So,
when you're here, give me a call. See you later, everybody.
Thanks a lot. Bye.
Good.
All right. Up next on our agenda, we have Club President Tricia. Are you with us, Tricia Smedley?
I am. Can you hear me?
Yes.
Okay. So thank you, Tom, for that great presentation. I know many of our members who are interested in spectroscopy appreciated that, and then hopefully some members that maybe are now interested because of what the presentation I just saw. So again, thank you, Tom. So I'd like to welcome the new board that was recently elected. The board member information, if you guys are interested, is located on our website, cfas.org. I'm going to drop the link here in our comment section, in our chat here. Now, we have two board members that are specifically there to serve as a liaison between the board and the members. And those two board members at large are named Eric Hoyne and John Pinto. And I'm going to put their names and emails in the chat as well. And now, if you have questions, issues, things that you want to bring up to the board, these are the guys that you're going to contact and to get the ball rolling. So it's important that you guys know that you have some fellow members that are specifically looking out for your best interest, and they are there to help you. So thank you, Eric and John, for serving once again as board members at large. We really appreciate your work. On to some more exciting news. We have our holiday party slated for Saturday, December 10th. We are going to be meeting at the planetarium again, in the same location where we had our September star party. And now we will be sending out specific room numbers and maps closer to the event We're also going to be having signs located around the planetarium to help guide you in. Now, weather permitting, we will be setting up scopes. So if you're interested in bringing a scope, looking through a scope, maybe checking out scopes, potentially to buy for yourself for Christmas, this is a really good time to not only come eat some free food, meet your fellow members, meet your board members, learn about the club, but also to view. That's really all we want to do, is look through telescopes and talk about space. So again, Saturday, December 10th is going to be the date of our holiday party for 2022. We plan to start setting up around 5 p.m. The event will start around 6 p.m. and we are planning to host a dinner around 7 p.m. Now, this year, similar to previous years, because we had so much luck with them in the past, we will be catering with Four Rivers once again. It's a barbecue joint. It's pretty good food. We're gonna make sure to have some vegan options, gluten-free options, and some low sugar options for the varied diets that are out there. Now, the most important thing to know about the food, because we want everyone to have some, is we would like to get an accurate head count. So we're going to be sending out emails and making posts in the closed Facebook page asking for people to RSVP. Family members, friends of yours are more than welcome to come. We would just need an accurate head count. So in the days, in the coming days, make sure to look out for an RSVP email so we can get an accurate head count. Also, in years past, we tend to have leftovers. And so if you're interested in the potential of taking home some Four Rivers barbecue leftovers, I suggest bringing some Tupperware, saran wrap, and or Ziploc bags, because we will not be providing that. And it's always tough to transport barbecue, as we all know. Again, weather permitting, we're going to have all of our scopes out. If you have any questions about bringing your scope out, make sure to contact our outreach coordinator, Douglas Woods, or my outreach@cfas.org, or myself, president@cfas.org. We can help answer questions. I'm not sure at this point if we're going to be turning off lights or not. That's something that we have tried to do in the past to make the parking lot a little darker. Again, more information to follow, so check out the Facebook page and our group's IO page. The last thing I'm going to bring up at this meeting is, before too long, our brand new education chair, Elizabeth Vega, is going to be sending out an interest survey where members can choose from topics they would like to learn about, vis-a-vis webinars, in-person workshops, so on and so forth. We really want to get a good gauge on what you guys are interested in, what kind of workshops you would be interested in attending. We really want to hear from the membership, what you guys are interested in, what you would like to learn about, what you would like to hear about. So again, keep an eye out for that in our closed Facebook group page and also the group's IO page. And with that, we are going to transition into astrophotos. And so I'm going to hand it back over to you, Frank.
Yes.
So let's see what the club came up this time.
All right. Thank you, Tricia. And quick note there, just to clarify, the board members at large are currently John Pinto and Mark Pernal. Eric Hoyne is our outgoing board member at large. So if you do have...
I stand corrected.
Okay. So if anyone has any feedback for the club, those are your points of contact. And you can find them either through the email aliases on cfas.org or through groups.io, where you can message fellow members quite easily. So, and with that, let's switch over to astrophotos, and let's see if I can figure out Zoom here successfully while I share my screen here. I think most of our imagers are here and can talk about themselves. Hang on while I share my screen. Share. All right. Hopefully you all see a beautiful picture of a moon. Holler if you don't. But
yes, we do.
Okay, good. All right, this one's from Ashton Guitard, and I believe you are here. So what I'm going to do is give you an invitation to unmute yourself. And if you'd like to tell us a little bit about your image here, how'd you do it? There's a whole lot of dynamic range going on here. Ashton, there should be a button to hit on your screen right now to accept unmuting. Zoom can be confusing. All right, Ashton, if your mic starts working, feel free to just talk over me, but you did send in some notes, so we'll go with that.
Can you
Oh,
hear
there
me
you
now?
are. Yes,
All right,
yes.
here we go. Excuse me, my mic was set to something that is not plugged in.
Okay, that explains it.
Alrighty, so yeah, I took this a few weeks ago, I think during our last crescent moon, and it's an HDR. It's made with 2 shots, one exposed for the illuminated side, one exposed for the unilluminated side, and then that was then cut out and then placed on top of an image, a copy of the image for the unilluminated side to give it that nice glow. And so you can kind of see a couple of stars right behind the moon there.
Yeah.
And yeah, so this was done in Photoshop. As I don't quite remember the exact camera settings of it. I know the shot for the illuminated side was taken at 100 ISO, and the one for the unilluminated was at 400, which I feel like you can kind of see that in the image, but maybe that's just me. But yeah.
Very cool. Yeah, I love how you can see the earth shine there and that glow around the moon there. It's a great effect. So well done. And this is also yours. You want to talk about this image too?
Yeah, so this is actually a bit of a special photo. This was the day I realized that I can take photos of the Milky Way from my backyard,
Cool.
which was quite a surprise to go out there and see that. I live kind of out in the middle of nowhere by Paisley, if any of y'all know where that is. So I'm right on the border of the Ocala National Forest, so pretty dark skies, as you can see. And at first I thought this, well, I didn't think this was a shooting star, because I saw this object passing through the frame here in person. I saw it out there. And what I believe it is a satellite that happened to turn its solar panels and reflect the sun back at me for a brief moment, and I happened to capture it like this because before it was bright and after it was bright, it looked just like a normal satellite. But yeah, you can see part of the galactic center right there. This was taken, yeah, again, not too long ago, probably a couple of weeks.
Very cool. Yeah, I agree with your hypothesis. It's probably a flare from solar panels. And I remember it was in the news maybe a couple of months ago that there was actually a new satellite being launched that was extraordinarily bright and did this. So how bright would you say that was? Like, what would you compare that to?
Oh, it was fairly bright in person. I would say probably around the brightness of Jupiter for just a brief moment. So it was definitely very, very noticeable.
Very cool shot. And I have some dark sky envy going on here. So thank you, Ashton.
Yeah, thank you.
Cool. Up next, Bob Santilla. So let me unmute you as well. I think, oh, did we lose him? We did, unfortunately. Let me just triple check, make sure you didn't change your name. All right, well, this is a gorgeous shot of the Milky Way, and he did send in some notes. So Bob Santilla writes, I'd like to share a recent photo I took of the Milky Way core while visiting Maine in September. That's pretty cool. It was taken with a Canon 5D Mark IV using a Rokinon f1.4 24mm lens at 14 seconds with an ISO of 1250. It was taken from the beach at a seawall in Acadia National Park, a little bit of a different scenery than here in Florida. Single shot edited in Adobe Camera Raw. And a bonus, Bob was also able to see the launch of a Falcon rocket as it was heading into space to deliver some Starlink satellites. So very different perspective from what we see here in Florida, being that far north. Unfortunately, he didn't get a capture of, he wasn't able to get a shot of that on camera, but the local papers were kind of wondering what was going on there. There's this weird thing in the sky and no one knew what it was. Everyone thought it was a UFO. But being from the Central Florida, we know what it is. It's just Starlink. So thank you, Bob, for the submission. Up next, we have John Starr doing some awesome deep sky work from Winter Springs. And John, I'm going to allow you to talk here if you'd like to talk about these images.
Gotcha. Thanks, Frank. Yeah, so these I took this shot and another shot, I think, that I submitted here. So this is with a Rokinon 135 and a ASI 1600 mono with on a Series EKG mount using an ASI Air Pro, and so I hadn't done this before. I normally have sort of this Esprit 120, and it's heavy. I don't have a I have to carry all my equipment out every night. I want to image and set it up like many of us do, and it's heavy and it's cumbersome. And so when when I know there's only a couple hours to image, I was trying to find a solution where I could still sort of do something without setting all that heavy equipment up. So this is super lightweight. I can just pick the whole thing up and carry it outside. And so that's kind of what I did. I only had a few hours over a couple nights. And so this image is about 10 hours sort of total over the course of a few nights. And so, yeah, so it came out pretty good. There's some weird banding issues that I've got going on shooting at sort of f 2.8. I've got to get sorted out, but I like how it sort of came together here. And
Absolutely.
this was shot from my backyard in Winter Park, so pretty heavily light polluted skies.
Yeah, and I can appreciate that. Even with 10 hours of exposure time, pulling out that oxygen emission data is challenging in light polluted skies. So nicely done. That fast lens, I imagine, helped quite a bit. So
yeah, for sure.
Cool. And we can see the Heart Nebula, the Soul Nebula, and the Fishhead Nebula kind of hanging off the bottom of the heart there. Very nice image. And you also sent in this one as well.
Yeah, so exact same setup. And so when one got sort of when this the Sator region here, the Gamma Cygni Nebula, when it sort of dipped below my house, I started shooting the Heart and Soul Nebula. So I was kind of shooting these the same nights. I only captured, it's a little late in the season to be shooting this, but I got 5 hours on this exact same sort of setup here. Again, sort of pleased with sort of how it came out. It's the first couple shots, and again, that rig with just the Rokinon 135, which I just checked, by the way, it's on sale. It's like 20% off right now, or the Samyang version of it is 20% off right now. So pretty affordable lens. Again, I'm really happy with sort of how it came out. First image here.
Absolutely, that's beautiful, and great processing as well. That's the Crescent Nebula up in the upper right there, is it not?
It is. Yeah, that's right.
Cool, very cool. Awesome image. Thank you, John.
Yep.
Up next, another John Pinto. And John Pinto, I think you're already a panelist and can talk whenever you want to, so I'll let you talk about the lunar eclipse.
So yeah, that's the lunar eclipse from just looking out my backyard window. That was probably about I'm going to say about 5:30 in the morning, because if anybody was watching it, you know that it was setting just before the sun came up. It was also really cloudy for a lot of us, and this is just a simple little iPhone SE 3rd generation, nothing special, just using the standard iPhone camera software, holding it very steady. And I think, Frank, you've got the next picture, which shows what it looked like just a little, maybe like half an hour later,
Yep.
when it started dipping down into the clouds, which from what I understand, that's what a lot of people saw. So just wanted to let people know you can do, beautiful photos with, very little equipment.
Very nice. Yeah, I slept through it. I really tried to stay awake for that, but I just nodded off, and now I'm kicking myself because it's not going to happen again for a while, right?
3 years.
Yep. All right, and I see Robert Santilla is back online. Did you want to talk about that shot at Maine some more? I'll let you take the mic here if you'd like. I think he's having some connection. Oh, wait. Try again. All right, I think your mic is live, Robert, if your mic is connected.
Okay, can you hear me?
Yes.
Okay, I don't really have anything to add other than if you have the opportunity to visit Maine, there really is some great observing along the coastline. It's just incredible being able to overlook a Bortles 1 area. Just really worthy.
Very cool. Yeah.
That's pretty much it.
All right. And I imagine all the constellations are in the wrong place up there, right?
Just a little different.
All right. Cool. All right, a few of my own here. So I was able to bust out my planetary imaging gear last month, and this is the best shot I got of Jupiter while it was close to opposition. So every year you want to pay attention to when the planets are closest to Earth, and that's the best time to image them. And if you can get lucky with some good seeing conditions, you can get a fair amount of detail without a whole lot of fancy equipment. So that's my Jupiter from this year. Also, this is my own shot of the Pac-Man Nebula, imaged in narrowband. So you're seeing the Hubble palette there, where sulfur emissions are mapped to red and hydrogen to green and oxygen to blue, and processed with a little bit of creative license to make it look a little bit more pleasing to the eye. So interesting object there, the Pac-Man Nebula, and same treatment here for the Wizard Nebula. It doesn't really look like a wizard unless you turn it on its side and really squint and use your imagination, but still a pretty object in its own right. And we also have our own Richard Wright. Let me unmute you, our outgoing president. How's it feel to just be able to talk about your images instead of running the show here? It must be pretty good.
Yeah, it's a different experience, that's for sure.
Cool.
Yeah. So yeah, this is Jupiter. Oh gee, when did I take this? Last week. Setting up a new scope and mount. Didn't expect the weather to be good. And it's like, I've got some stuff to do. And I did alignment, and I thought, oh, let's just point at Jupiter. And Jupiter's right in the middle of the sensor. So I'm like, oh, I'm really tired and I want to go to bed. Let me just put in an eyepiece. And I put it in an eyepiece, and it's like, oh, wow. This, of course, it was a deep sky camera. So I didn't really take a picture of Jupiter. It just looked like a star. So I put in the eyepiece, and I'm like, oh, wow, there's the red spot and a shadow transit. And I'm like, oh, if I don't do it, I'm going to hate myself. So then I got out my Power Made and high-speed camera and plugged it all in. And yeah, I was pretty happy. The seeing was particularly good that night too. This is a 6-inch refractor, so it's not a giant telescope, but the 6-inch refractor holds up pretty well when you have good seeing on the planets. I thought I used a 4x Power Mate, and I had a Player One Neptune C2, so a color Player One high-speed camera on the back, and process it with Auto Stacker and a couple of things I cobbled together.
Cool. Yeah, that's amazing for a 6-inch. Wow.
Yeah.
So yeah, tell me about that Player One camera, by the way. That seems to be what a lot of the cool kids are using these days. Have you found that it's really helped your imaging of planetary objects?
Yeah, I had a color ZWO, and I sold it to somebody in the club. I hope they're very happy with it. And I got a mono Player One. I was in the market for a mono camera for doing solar stuff with the HA filter, and I really liked it. Very good, build quality, that sort of thing. And I still do, Astro software development. I really like their SDK. And I can basically judge a camera's build quality by are they willing to invest in software engineers, or did they hire somebody's nephew to program something? And they had a really nice SDK, and they were very responsive. Their engineers seemed, I was impressed. So I thought, well, let me try one of their color cameras. I have a 174, but I would like something a little higher resolution. The 174 is a great color camera with anyway, this is why I'm not president anymore. I could talk all night. Yeah, it's a great camera. So I have 2 of them now, and I'm very impressed with them. They don't give me any trouble. I'm never like, oh, the camera stopped working or anything like that, and the software support is good. So yep, I'm pretty happy with them.
All right, I think I might be asking Santa for one of those. That's a good one.
Yep.
And look, a helicopter.
Yeah. So this is my early morning this morning. Drove out there and paid $40 to park in the grass somewhere so that I could be across from the launch. And me and a whole lot of other people waited it out. And I just I had like over 300 pictures, and I was like, I can at least pick one of these that are pretty good. And I'm like, what is this little thing up here? And if you zoom in on it, it's actually the silhouette of a helicopter. And I have dozens of photos. I was on the side of I guess I just happened to be on the right side of the launch, but that helicopter is there. somebody said it must be tourists. They must have paid a lot of money for that, but I suspect it's actually NASA,
Yeah.
you know, monitoring it. They've got cameras on the bottom of that, and they're watching the launch and all that sort of thing. But it's like, hey, I've seen lots of pictures of this launch. Who else caught the helicopter there in the middle? So yeah.
Man, that can't be safe. I mean, I would not want to be in a helicopter.
That is I mean, if that blew up, that whoever's in that helicopter is a goner. Yeah, that would.
Yeah. But fortunately, it went smooth as butter. So
Yes,
that was amazing to watch. And
It did.
Yeah.
It was great to be there too. The sound is amazing. If you ever get a chance to go, you should go.
absolutely. Oh, some deep sky stuff.
Oh, this is me too. Yep. Last new moon, we had a really good streak of good weather. I spent 4 nights down at my dark sky camp in Okeechobee, and I collected this over 3 of the nights, about 6.5 hours total, along with some other stuff that I'm still working on. This was astrophysics stowaway with the flattener and QHY 128C one-shot color camera, and on a Paramount MX Plus. I was really happy with what I liked about this was all the dust. You know, M42 and the Running Man are popular targets, big bright emission objects. And NGC 1999 is the Keyhole Nebula, and it's in this picture, but it's very, very tiny. And I can't even see it looking at my computer screen now. But just all the dust that was around this, I was really like, oh, I got all the emission and I got all the dust together. So I was very happy.
Yeah, that's a very unique view of this whole region. I never knew that dust was there, honestly. So that's pretty cool.
Yeah.
Yeah, and before we move on, just a quick thank you for your years of service as president of the club. You know, you did a great job, and we got big boots to fill here. So,
no, you're welcome. I'm going to hang around. You know, so I'll see you everybody in December.
All right. Yes. Well, I'll be in person for the holiday party again. Mark your calendars, December 10th. And of course, we'll have more details sent out via groups.io shortly. So you don't have to take notes. That'll be coming soon. And that is the end of our astro imaging segment. Let me stop my sharing, and I'm going to hand things over to John Pinto for What's Up in the Night Sky. John, you here?
Yeah, all right, Frank. Thank you very much.
All right.
Let me get my screen up here. Okay, and we'll get started. Yeah, right. And I like to use my laser pointer. Okay. So unlike all of the other presenters, this is for the folks who are just starting out. And we all have to start somewhere, right? So when I was first starting many moons ago, my biggest problem was like, where is stuff in the sky? And so that's really been my focus now for a few months with these presentations, to kind of get you up to speed with where you can see in the sky, what's rising in the east, and what things you can observe fairly easily as the month goes by. So let's get going. Okay, as I always say, the sky is huge. You do need to have some way of like figuring out just how big stuff is. So I like to use this graphic to have you experiment with just how big is the Milky Way, the Big Dipper, sorry. And you will need to know where directions are, like where's east, where's north, where's south. In case you don't know, the sun rises into the east and it sets in the west. So if you could figure that out, pretty much north and south is on your left and your right if you are facing east. So that's, you know, wherever you're observing, you know, you definitely want to know where your directions are. Website I like to point beginners to, great site, What's Out Tonight. It's where I'm going to use the charts from them so you can kind of see how to use it. And it's all free. He has video tutorials in case, you know, my explanation is not that great, which is probably true. But this is a great site for beginners to get started with. Okay, I'm going to spend a few minutes more on this than I normally do because I don't think I really explained, for people who are just getting started, what we're seeing here. So what I'd like to explain, why I like this image, now this comes right out of Sky and Telescope magazine, just blown up really large, is it kind of tells you what you're seeing in the sky, why are you seeing it in the sky, where you're seeing it, okay? So let's just start with the Earth over here. So the Earth moves around the sun this way, okay? And the Earth also spins around in the same counterclockwise direction. So on this side of the Earth, when you're, standing over here and you're looking right at the sun, okay, so this is daytime. So this is the daytime side, and this is the nighttime side. Now, because the sun is spinning, the Earth is spinning around this way, so here's daytime, 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 oh, it's becoming night. So this is basically when the sun is setting, right? You're going to be like over here on this part of the Earth. So the things you're going to see near the sun are going to be over here, right after sun sets in the west. Okay, so right now there's really nothing there, right? Mercury and Venus are behind the sun. It's way too bright, and you're not going to see them. Even towards the end of the month, shows you the whole month of November. So we're right about here, all right, in this month-long movement of each of the planets. And this is the end of the month. So at the end of the month, Mercury and Venus will be here, but also at the end of the month, Earth is going to be over here. So you're not going to see it because it's way too close to the sun. Okay, so that's sunset. You spend the night, you're staying up all night long. The Earth is spinning, spinning, spinning. Up, here comes dawn. So at dawn, you're going to see this stuff in the east on this side. And again, there's nothing here. So there's not much going on right now in the morning sky near the sun in the east. But as it's getting later and later in the night, sun is set, and here's Mars over here. Now that means that Mars is a little bit towards the east, but as we get towards the end of the month, right, Earth will be here, Mars will be here. It'll be almost directly opposite the sun. And that makes sense because as we're going to see when we go over the events of the month, Mars is going to be closest to the Earth right at this point, right at the end of November. It's not at opposition, which is a slightly different concept, but they're usually very close to each other when they're closest, when they're at opposition. The other thing that this kind of teaches you is what we call retrograde motion. So as the Earth is moving around here, it's moving a lot faster than Mars, right? This is a lot larger arc than this. So as the Earth is moving here, Mars is not catching up with us. So Mars is going to actually look like it's moving backwards against the stars. And we'll explain that when we show the image. Okay, so that's Mars, Venus, Mercury. Now, over here, we're going to look at the outer planets. And because the solar system is so huge, this entire huge portion of the solar system fits in this little tiny little circle here. So you have to imagine Earth is here, so Earth is like about here. So at night, what you're going to see is Jupiter pretty much due south for the most part, and Saturn will be sort of setting in the west. Uranus and Neptune, if you know where they are, they'll be up in the night sky as well. Between Jupiter, one on one side of Jupiter, one on the other side of Jupiter. In between Jupiter and Saturn is Neptune. So that just kind of gives you an idea of when you look out at the sky and you're looking at the planets, like where are they really in the solar system and why do I see them where I see them in the sky? So I always like to look at this. As Tom was saying, sometimes you need to hang your concepts on something, visually understandable. Okay, so what are we actually going to see in the night sky? So here's your evening sky. About 7 o'clock is when astronomical evening starts, and it's starting to get about as dark as it's going to get. Now, a lot of this that you're seeing, you probably are not going to see if you're in a light polluted sky. So I'm just going to point out some of the brighter things that, again, for beginners, what should I start learning? And I always say, learn the bright stars, the bright constellations, and where the planets. So coming up, we're beginning to start to see the beginning of the winter constellations. So Taurus and Auriga are considered winter constellations. And the bright star in Taurus is Aldebaran. The bright star in Auriga is Capella. The other thing that's really interesting, and Tom brought this up, is the Pleiades. You can start observing naked eye, just a little bit above Aldebaran. But you can also take out your binoculars and you'll have a great, in fact, that's probably the better view of Pleiades with binoculars. Another thing that we're going to be talking about in our events is Algol, the demon star, probably the most famous variable star in the sky. And we'll point out when it's going to dim significantly, enough that you can actually notice it, and when it will start getting brighter again. So that's always an interesting evening of observing. Pretty much overhead is what's called the Great Square. Now, you probably won't see this unless you know exactly where this is, because these are not very bright stars. But if you can identify where that is, this is where the Andromeda Galaxy is. And you can see that in binoculars, but you will need somewhat of a dark sight to see that. Jupiter will be, like I said, pretty much almost due south. It'll be the brightest thing in the sky. And then to the right of it will be Saturn. It's sort of in the southwest. Okay, so that's, if you can start with that, you're doing great. One other thing to note is what's setting is our summer constellations. So the Summer Triangle, Vega, Deneb, and Altair. Again, the brightest stars in that part of the sky. And we're going to basically be saying goodbye to the summer constellations, even though we're in the fall. These are considered the fall constellations. These are considered the summer constellations. I am a morning person, so actually most of my observing is in the morning. Right now, about 5:30 in the morning is just the end of astronomical night, but it's still dark enough that you can do some great observing. So in the morning, what's rising is Arcturus and the spring constellations. And if you don't remember how to find Arcturus, find the Big Dipper, which will be in the northeast. You follow the handle around, and the bright star you come to is Arcturus, and you continue it around a little bit further, and you'll see the bright star Spica. So you'll already now know two constellations, Boötes and Virgo. The other thing that is fairly easy to spot is Leo the Lion. So the way you find Leo the Lion is, again, you find the Big Dipper, you find the two pointer stars, which normally you use to find Polaris, but you go the opposite way, and it'll point you to Regulus, which is the the heart of the lion. And this sickle shape you probably won't see, but what you probably will see is Algeba, which is the star here. You might be able to pick out Denebula, but again, you'll need a dark sky to actually really see this constellation of Leo. The other thing that you'll notice is we are losing the winter constellations. Okay, so we saw that, where is it here? Auriga and Taurus were just rising in the east in the evening, but in the morning they're starting to set. But you can still make out all the winter constellations, your Gemini, your Auriga, your Taurus, your Orion, Canis Major and Canis Minor. And that's also what's called the winter hexagon. So again, your brightest stars are Sirius, Procyon, Castor and Pollux, Capella, Aldebaran, Rigel, with Betelgeuse right in the center. And if you can't find Orion, just look for the 3 stars in a row, the belt. It's very prominent feature in the sky in the west. You probably can't miss that. All right, so let's get on to the sky calendar. What are the significant events coming up? So tonight, last quarter moon. If you don't know what does that mean, it basically tells you when the moon is going to rise, when it's going to be in the south, and when it's going to set. So as we get to each of the significant moon quarters, I'll explain kind of what that means. So in the last quarter moon, the moon rises around midnight, and it comes up in the east, right? Everything comes up in the east and sets in the west. The moon rises around midnight in the east. It'll be high in the south at sunrise, and it'll set in the west around noontime. So this is actually something you could see during the day between dawn and noon. It'll be in the southwest to western sky. On the 17th, if you can get up before dawn, the moon will just be 6 degrees from Regulus. Now, why do I highlight this? Because again, one of the hard things for a beginner to learn is like, where is stuff? So pretty much everybody can find the moon, and Regulus will be the brightest star near the moon, only about 6 degrees. And this 6 degrees, if you go back to the earlier slide where I was talking about sky measurements, you basically stick 3 fingers up, and that's about 6 degrees. And you'll be able to see, you stick your hand up in the sky, see where the moon is, and Regulus will be about that far away from it. So again, you'll learn where Regulus is tomorrow morning by just looking where the moon is. Friday is the Leonid shower, first thing in the morning, again, before the sun rises. Now, the moon will be up as well, so you may or may not see anything, but hey, if you're up Friday morning, it doesn't hurt to go outside for a few minutes and see if you can see a meteor shower. I mentioned algol before, so Saturday evening, algol will have a minima Saturday evening around 10:25. In the evening, it'll be in the eastern sky. What you definitely want to do is find algol before this. So, 7 o'clock, see how bright it is, go out every half hour or so and watch it get dimmer and dimmer and dimmer. 10:25 will be at its dimmest. Depending on how late you want to stay up, you can stay up afterwards and watch it brighten up again. Usually takes about 4 to 5 hours to dim, 4 or 5 hours to get brighter, back to its original brightness. But if you can observe any of that, you'll get hooked on variable stars. On Monday, before dawn, again, for your early risers, the moon will be 4 degrees from Spica. So again, you don't know where Spica is, get up Monday morning, look for the moon, and Spica will be the bright star right near the moon. Wednesday the 23rd is a new moon. You won't see that at all because that's why it's called new. It's on the other side of, it's between us and the sun. So the moon will be dark and we won't see it. That also means it's a good time to do observing of dimmer objects because the moon won't interfere with your observing. The 24th, next Thursday, can't believe it, it's Thanksgiving, and we can all give thanks for the beautiful heavens that are above our heads. The Monday after Thanksgiving, the evening, the moon will now be only 6 degrees from Saturn. So again, if you're not sure where Saturn is in the sky, wait till the Monday evening after Thanksgiving and the moon will be right near it. It'll be the brightest thing near the moon. At the end of the month on the 30th, it is the first quarter moon. What does that mean? It means that when the sun sets, the moon will be high in the south at sunset. And it will set in the west around midnight. It is also the night when Mars is closest to the Earth. So if you have a telescope, this is a great time to get out there and to view Mars at its closest approach to the Earth. I'm only going to do a few days in December because we are going to be meeting on the 10th. So there's only a few events in December to mention before we all get together. So on the 1st of December, the moon will have moved from Saturn over to Jupiter. So again, if you don't know where Jupiter is, I mean, it is the brightest thing out there. The moon will be right next to it on the 1st. On the 6th in the evening, the moon will be between the Pleiades and the Hyades. The Hyades, you may not notice it, but the star Aldebaran is in the same part of the sky where the Hyades is. So if you can find the moon on the 6th, the Pleiades will be up near the moon. You can find the Pleiades from that, and you'll definitely be able to find Aldebaran because it'll be the brightest star near the moon that night. Wednesday, the 7th of December is the earliest sunset of the year. So it'll be you'll be able to get out earlier in the evening to do your stargazing after the sun sets. Also on the 7th, this is kind of an important thing. If you can stay up till about 10:30 in the evening, the moon is going to skim past Mars. It's going to get so close that you probably won't even be able to see the distance between them with your naked eyes. You may have to get your binoculars or your telescope out to actually see the distance between the moon and Mars. Now, if you were farther north of us, say the New York or Ohio or anywhere northwest of us, the moon actually occults Mars, which means the moon will actually cover Mars. So Mars will blink out. If you were out there, you would see Mars for a little bit. The moon would go over it. Mars would go away, and then half hour, an hour later, all of a sudden Mars pops out on the other side of the moon, that's always a cool thing to see. But here in Florida, we will not see an occultation, but we will see they get very, very close. I think that would be an exciting thing to actually witness if it's got clear skies at night. A little bit after that is the full cold moon at 11:08 in the evening. Again, the full moons rise in the east at sunset. They're due south around midnight, and they set in the west at sunrise. This is a busy evening because just a few hours later, Mars is at opposition at 12:36. That should say a.m. Sorry about that. Thursday, the 8th, at basically a little bit after midnight, Mars will be at opposition. So again, a great opportunity to observe Mars as it is opposite us from the sun. And then, of course, Saturday the 10th, we'll all get together at the CFAS Winter Star Party being held in the planetarium classrooms. And I am hoping to do an outdoor sky tour so we don't have to use these planisphere images from what's out tonight. We can actually go outside. I'll have my laser pointer and we can actually point out some of these things that we've been talking about. So you can go from what you're holding in your hand, either a printout or an app or a planisphere, look it up in the sky and you can see how to take this tiny little image you're seeing in your hand and how large it is up in the sky. And hopefully that'll be of interest to some of our newer astronomers. Again, my little page of free internet resources that I always point people to that has great information for people who are getting started at all levels, really. And of course, I always promote our CFAS Facebook public page for those of you who are not members, or even if you are a member. We try to post a lot of beginner information here, things to look at in the night sky that particular evening, interesting posts from some of these websites that we follow, and hopefully it will, you'll find that of interest and help you to learn the sky as we move along through the year. And that's it, and we'll see you next month down at the Star Party. Thanks, Frank.
Thank you, John, and looking forward to doing that in person next month. Before I hand things back off to Tricia, we had a late question come in for Richard Wright about the astrophotography there. Are you still there, Richard?
Yes, now that I found the button to unmute myself.
Cool. Yeah, we had a question from Bob Santilli. He wanted to know what setting you used on that launch shot of yours.
Oh, it was so Canon EOS RA I had 70 to 200 millimeter Canon f2.8 lens, but I had a teleextender on it, the Canon 1.4 teleextender, and it was ISO 1600, and it was set to f5.6, and I think it was a thousandth of a second shutter speed. I had my finger on the dial and I shot a couple of hundred pictures, and I was basically scrubbing back and forth on the exposure because I knew it was going to be a lot of stuff overexposed, and so I was trying to get some things under. Anyway, I was playing around with it, but that shot, yeah, that's it. A thousandth of a second, f5.6, ISO 1600, and basically the effective focal length was 420 millimeters. So.
Cool. Thank you, Richard.
Yep.
Yeah, that thing was unexpectedly bright. So capturing that at all, I think, was quite an accomplishment. Cool. All right. So next month we have the Winter Star Party at the planetarium. More details for that will be coming out shortly. And in January, we have confirmed Tim Russ will be coming back. Originally, we had Tim Ross from Star Trek Voyager scheduled for this month's meeting, but Hurricane Nicole messed up everything, and he was not able to join us tonight due to a work conflict. But January 11th, he will be back talking all things amateur astronomy and science fiction. So that'll be fun. And to wrap things up, Tricia, do you have any parting thoughts?
Well, thank you, Frank. I think it was a great meeting. Thanks to everyone who came out and attended tonight. I know we're going to be getting the recording of this up on our YouTube page pretty soon. So if you guys want to send this out to some friends and family, maybe future CFAS members. Thanks for uploading it soon, Frank.
Yep, will do. All right, and it is 9:01. We're 1 minute late. I'm sorry, but close enough. All right, watch your emails for more details on December 10th, and we will hopefully see most of you live then. Until then, keep looking up.
Thanks for coming out, guys. Bye.
Thanks, Frank. Thanks,
Bye.
Trish.